Welcome everybody. In this video we're going to use what we learned in the Biophysics and Physiological modeling book to try to understand the COVID-19 pandemic. And in particular what we're going to do is try to understand the epidemiology of the outbreak. And all that means is the mathematical modeling of an epidemic. Alright, so the kind of model that we're going to do is just about the simplest possible model it can be. Here it is, we've got two possible states for the population, right? The population, you can either be a susceptible person or an infectious person. Those are the only two choices. And so if you're susceptible, the only thing that can happen to you is that you become infectious. And the model says that the rate that happens is given by a rate constant k, and that rate constant k tells you how often an infectious person infects one of the susceptible people. And it depends on, this rate depends on how many, so Ni is just the number of folks in this infectious box. Alright, so if that didn't make a lot of sense to you, then what I recommend you do is go to the website for this project, which is at circle4.com/biophysics, and there are free sample chapters. So if you go here and you click on the free sample chapters, you get to the chapters page. Here's chapter 1, chapter 2, and chapter 3, which we're going to talk about next. And then chapter 12, which is way down here, actually builds on stuff that was in chapter 3. Alright, so let's talk about chapter 1. So chapter 1, here's the cover page. You'll notice that it has on the cover a finite difference diagram, pretty similar to the ones that we're going to talk about today. And it's all pretty much, it introduces you to this marble game, right? And the marble game, where are we? Here's the marble game, right? There it goes. Let me make that bigger. There's the marble game. And it's got 10 marbles in 2 boxes, and all they do is the marbles can jump from there to there, or they can jump from there to there. And it turns out it's amazingly useful for trying to understand how molecules work in physiology. Alright, here we go. So, the thing I wanted to say about chapter 1 is that it's an introduction to using Excel, right? So it starts out really at the beginning, which is how does Excel work, and we talk about how to put formulas into Excel and what they actually do. So if you're new to Excel, you definitely should start with chapter 1. And even if you are familiar with Excel, it's probably worthwhile looking through chapter 1 just to see how we're going to be using it. Chapter 2 is about algorithms. Now an algorithm, the point of an algorithm, it's a recipe for how to fill out the spreadsheet. And it has parts, right? So parameters are like the utensils you use for cooking. They don't change. Variables are things, they're the ingredients for the recipe, and they do change. Step 0 is like setting up the board game, the rules for setting up the board game before you start. And then step 1 is the rule for how you describe how the game progresses with time. So that's chapter 2, and again, it's kind of an important building block for this. Chapter 3 is primarily about these finite difference diagrams, and again, here's the marble game thing. We've got marbles can jump from box 1 to box 2, and that's what this arrow is about. They can also jump back from box 2 to box 1, and that's what this arrow is about. And it turns out our models of COVID-19 are actually even simpler than this because the arrows only go in one direction. We're now ready to get to chapter 12. So here's chapter 12, and we have the FD diagram that we've already talked about. We have our 2 boxes, one for the susceptible portion of the population and the other one for the infectious portion of the population. The rate at which people go from susceptible to infectious depends on the rate constant, which is how often an infectious person can infect somebody who's not, and Ni, which is the number of people who are infectious. So that's the thing that I just want to talk about a little bit more. Let me go back to PowerPoint, make this big. Alright, so again, if I do this, the thing about this is we have, that's the rate, and that goes down here, right? That's the exact same thing. Ri is a thing that we're going to be talking about. It's the infection, so I, that I goes there, right, and rate. So the reason it's a double letter is because Ri is the infection rate. Alright, so Ki, as we said, is the infection rate constant. So I've underlined I here because there's an I in the rate constant. And the square parentheses, sorry, the square brackets around the equal sign mean that Ki has units of 1 over D, and the D here stands for day. So Ki is a rate constant for getting infected per day per infectious person. So that's Ki, and then the last thing we need to talk about is Ni, which is the number in box I. And again, this thing means has units of, and it has units of the number 1. It has no units, it's just a counting number. Alright, so that gets us back to Chapter 12, so there are a couple of formulas. So here's the formula that we've already talked about. We're going to need that for doing our spreadsheet, and you should read through all this stuff. This is the other formula that we're going to need, which says that the new number infectious is equal to the old number infectious times the infection rate times the amount of time that we're thinking of. So this delta t, delta is a Greek letter, and the lowercase delta, which you may not have seen if you're not familiar with lowercase delta, I have a video online that you should check out called The Greek Letters Go Green. And so delta t here is a small step in time. So I call it, and the normal name for this kind of thing is a time step, right? Because it's a step in time. So the new number infectious is the old number infectious plus the rate that people get infected times the amount of time that we're thinking about. All right. So question 12.1 says write out a complete finite difference algorithm including unit checks for how to do that. So rather than going through that in a lot of detail, chapter 2 talks about algorithms and chapter 3 talks about how to write finite difference algorithms. Let me show you the model answer. So here it is. So it's got, here's the algorithm, and param dollar, it's not a wannabe wrapper, right? The dollar is to remind you that we have to use the dollar sign for things that are in the parameters column. Anyway, so the parameters are things that don't change, and so the first one is delta t, the time step. It's in days, right? The format here is actually quite important. So we're saying that the time step has units of days and its value is 1. Ki is the infection rate constant. It has units of 1 over days, so inverse time, and its value is 0.03, 0.3, and the number infectious at the beginning of the model, N0, is 10. So we're going to start with 10 infectious people. Each one of those infects other people at 0.3 people per day, right? So after just over 3 days, you'd expect that they'd infect somebody else. The variables, right, the things that are going to change in the model are time and days. The thing that we're going to measure and compare our model to experimentally is the number of people infected per day, which is Ri. Ni is the total number infected. Step 0 is setting up, and so we set time to be 0, right? The new here means the current time, and the current value of the number infected in step 0 is going to be the value over here, right? So I think that makes sense. And then in step 1, what we do is we increment time by the time step, right? So the new time is the old time plus the time step. The new rate of infection is the rate constant times the old number infected, right? So in step 0. And the new infected number is the old infected number plus the rate times the amount of time that's elapsed. There are unit checks in here, so this is the formula that we've already talked about. It has units of, Ki has units of 1 over days, Ni has units of just 1, and so when you multiply that you get units of per day, and the rate of infections is given in per day, so that's good. Alright. The other equation that you need to just double check the units is the new number infected is the old number infected times the rate times time. So number infected just is 1, the rate is per day, and time is in days, right? So these two units have to cancel and give us back no units, right? The units of 1. And then the other part in the exercise is to write out by hand how to do the algorithm. So again, I go through how to do this in chapter 2 in a lot of detail, and in chapter 3 for finite difference things. And so you should make sure that you understand how to do this by hand. Alright, so the next thing that I want to do is to just show you how to do the problems. So let me go back to chapter 12 and read the problem. There we go, that's chapter 12. Alright, so the question is, write the algorithm. So I just showed you the algorithm, and I've just said this YouTube video, I'm going to post that link, will work to it when I get the video done. Then what you need to do is open this pre-formatted spreadsheet. So if I click on it, it'll open a pre-formatted spreadsheet, and I'm going to open it. And so here's Excel loading, and you have to click on enable editing to be able to edit it. And so what it has 2 blank graphs, and what we need to do is put our algorithm into the spreadsheet. So what you should do is open the where are we? There we go. Open the sample model answer, and you can follow along reading the algorithm, because it will probably make more sense if you look at the algorithm while I describe what's going on. So, Excel. So here we go. We want to put in, so let's just explain. We have numbers here for delta t. So the delta t in days is 1 in the parameter column. Ki is 0.3 and it has units of per day, and n0 is 10. The time in step 0 is 0, and the number infectious, see, it's a formula that links back to this one. If you have trouble with this, again, go back to chapter 1, and it kind of explains how the Excel stuff works. What we want to do now is, in step 1, we need to fill in this cell, and the instruction is that the new value equals Ki, and because this is a parameter, I need to hit F4 on a PC. On a Mac, you have to type in the dollar signs separately. So you need $A, $5 for this cell, which is in column A, row 5, and then multiply by NI old, which is that cell. And when you hit enter, it does the calculation, and so 0.3 times 10 gives you 3. Then in the next one, what we do is the new number infectious is equal to the old number infectious plus the rate that we just calculated times the time step. And again, I need F4 to get the dollars for A, $3. Alright, and so that's the whole algorithm, right? So we can now fill in this spreadsheet just by highlighting left click drag across the 2 cells, and then move. See how the cross here is an open cross? I then want to move to a closed cross when I get to that little blob, and then left double click, and you'll see that it actually fills in this spreadsheet and populates the graphs. Now, before we move on, I guess we should talk about the graphs and what they are. So the way you should read graphs is make sure you understand the axes first. Time t in days is on the x-axis. The y-axis is the new infection rate, RI, as confirmed cases per day, and we'll talk more about what that is, but I think it's fairly obvious what that means. The second graph has, on the y-axis, it has number infectious, and on the x-axis it has time. So even though they look like they're the same shape, they're actually telling you different things. Okay, now the instructions say do that, but you have to reduce, right? Reduce, oh, I need my pen. Reduce, I need the highlighter, there we go. Reduce the time step, right? And add enough steps so that the curves reach day 19. So at the moment we're at time 19, but I need to show you something that's kind of tricky, and you might not have noticed this before. I'm going to just fix the size of these axes because you'll see why. But I'm just going to do that now so I don't confuse everybody. I'm going to make the vertical axis have a maximum of 1000, and I'm going to make the time axis have a fixed time of 20. Alright, and I'm going to do the same thing here. I'm going to make this have a fixed axis, and I can't remember, so I'll just guess. Where are we? There we go. Axis options. I'll make that, let's say, I'll be generous and say 10,000. Yep, and I'll make the time axis have a maximum of 20. Alright, so we have that. Now, what do we want to see what happens? Well, what I need to do is add more things, and it turns out we're going to need a lot more than you might think. So I'm going to drag this down, and it might take a little while. I'm going to go down to 2003. I guarantee I'm going to go too far, but oh, I already did. 2003. There we go. Alright, so it's filled in the whole spreadsheet down to there, which is a lot. And all it's done in these graphs, because I fixed the axes, is just added some extra points. Now, what I want to do now is just talk about what happens when you change the time step. So at the moment it's one whole day. If I make it half of a day, you can see that both of the curves, right, this curve and this curve, both changed. Now, we don't want that to happen. We want our model to not depend on the time step that we're using. So if I make it like 0.1 of a day, so a tenth of a day, see how it still moved? Let's try 0.05 of a day. It moved a little bit. Let's try 0.02 of a day, and it moved just a tiny wee little fraction, and then 0.01 of a day, and you can see it finally didn't continue to move. So the whole point about that is that because we're using this thing where we're changing increments, we need to pick a small enough time that the answer that we get doesn't depend on the size of it. And it turns out for this particular problem that we need a really surprisingly small time step. It needs to be 1/100th of a day to make the curve pretty much match up with what would happen if we made it infinitely small. Alright, so I'm going to save this thing. This is one of the things that you should remember to do. So it says read only. Oh, that's no good. Let's go back. File, save as. And I want to put it in my thing that I'm working on, and I want it to go with the question that we're working on, which is question, I think it's question 2. Question .12.02. Let's just check. Sometimes I like to keep the description of it so we know what it is. Let's just save it. And I'm going to go back and check. Alright. Oh, not that. I want that. What are we doing? 2. Yes, so we are doing 2. And it says record your graph for the number infectious. So here we go. Here's our record your graph for the number infectious ni as a function of time. And it says reminder, that was what we were just talking about. The time step parameter needs to be small enough that it doesn't affect the model. Alright, so that's what we've just done. So I could then save this, right? If I go click and then do copy. So how do I do that? Copy. Control C is the way I usually do it. Control C, and then I could paste it into a Word document as a picture, right? That's the way that I get my students to do that. That's all explained in chapters 1 and 2. All right, so let's get back to the exercise. We have make a copy of the two graphs and change the vertical axis to a logarithmic scale. Okay, so what's all that about? So I want to save this for the next part, so I'm going to save this as question 2b. It's always good to save your work as you go along, and it said make it a logarithmic scale. So if I left double click on this vertical axis, yep, there it goes. Down here you get format axis, and down here there's logarithmic scale. So if you click on that, you get a log scale, and you'll see you get a straight line. And for the other one, I forgot to make copies, but it doesn't matter because I already have done this. So, but when you do it, make sure that you make a copy of the graphs before you do this. Anyway, how do you do that? You do Control C and then you do Control V. On a Mac, you have to use Command. And here, what I can do on this is left double click, and I get format axis, and I need that part and axis options. And then if I click logarithmic scale, you'll see that this one, the number infectious, just like the one above it, they're both straight line graphs. And because these are semi-log graphs, which is something we talk about in chapter 2, the straight line means that it's an exponential growth. And that's one of the things that we'll actually be talking more about. Okay, so I'm going to save that. And then let me go down, check. All right, so question, and then it says, what can you conclude? Well, I think I just told you what you conclude. Question 3 is a calculus question. If you don't have calculus, you can skip the calculus questions. If you do have calculus, which I think is a very cool thing, you can figure out how to get to this equation. And it says use the format that's in chapter 3. So I'm not going to go through that in this video, but if you have calculus, you can actually prove that this is the analytical solution for that, and then you can use derivatives and you can find that the rate of infection is given by that. Question 4 is actually pretty straightforward. It's so simple, I thought I had to say this. It's not a trick question. You just substitute this equation into this equation, and you'll find that you get the correct answer. The folks who have calculus already got that one. All right, so that's question 4. And the next thing that we want to do is talk about, let's see, what's the next one that I wanted to look at? Question 8. Okay, so the other questions are definitely worth doing, but I know from my students they usually have trouble with the Excel stuff. So let's skip ahead to question 8 and just quickly go through that. And so what this one is about is we're trying to analyze and compare the idea of exponential growth with actual data. So I found a place on the web at the European CDC, and I put it into the spreadsheet. So if I click on this, it'll open another spreadsheet, and that spreadsheet already has, so let's open it, and we're doing question 8. So what I'm going to do before I forget, yes, I'm going to enable editing, and I'm going to do File, Save As, and I'm going to give it a name, put it in that same directory. I'm going to give it a name, question BPM, and I like giving them systematic names so I can find stuff later. It's always good. Question 1208, and we'll do A. Alright, and it's the USA day 19. Right, so in fact this data came from the 19th day when the number of people infected was not 0. So it's not since the first infection, because we don't really know when that was. So this is day 19 for the model. Alright, so we're going to save that, And the question, let's go to the question. The question says, open that thing, and it tells you that the data that's in there, so let's just have another look at this. The data that's in here, these dots are USA data, and these dots are the number of people who were infected every day for these first 19 days since February 27th, and remember there was a leap year. Alright, so 6 on day 1, 1, then 6, then 3, then 20, then 14, then 22. And, you know, the pattern at the beginning seemed kind of, but as time went by, you can see that the number of cases, confirmed cases of infection per day, new infections, started to go up. And what we want to do here is try to analyze that and see whether it matches up with our model. Alright, so we have in part A, it says add an exponential trend line to the graph and check the options for display equation on chart and this display R squared. So that'll make sense when we start doing it. And then it says record your graph, right? So record means cut and paste the picture as a picture into a Word document. That's the way I always get my students to do it. Alright, so that's what we want to do. We want to add an exponential trend line. So here's how you do that. So you have to left click on the data and then right click on it and do add trend line. So here's add trend line, and here it goes. So, and the kind that we want, see, a straight line doesn't work at all. What we want is exponential, and you'll see it actually looks kind of close to the shape of the data. And it then also said display equation on chart, so select that checkbox and select the display R squared. So that's the formula. This little box tells you the formula that goes with the dotted line. And you'll notice that it's an exponential. There's 2.0173. E is the exponential number, Euler's number, raised to the power of 0.3365. Alright, so that's that. And then it says record that graph, so I'm just going to save it. But what you should do is file, save as, save. And then B, let's have a look back at our thing. B says record the model parameters you can obtain from the Excel trend line. And so the way that works is you need to look at the trend line, and I was just talking about the numbers. The first one you should do is the exponent. The exponent actually goes with the rate constant, right? So if you look at this, it's a number at the front, and then the exponential number E, and then a number times X. And the X, because Excel always uses Y for the vertical axis and X for the horizontal axis, the X is actually time in our case. So that means go back to the formula that we're fitting it to. We're fitting it to equation 12.6, and probably the easiest way to see this is for me to zoom in and write the equation underneath it, the equation that Excel fit to the data, which was y equals 2.0173 e to the 0.3365x. Now, the way to understand how the fit works is to kind of match these two guys up. So, as I said before, x and t match up with each other, which means that this 0.3365 matches up with Ki, the infection rate constant. The two E's are obviously the same thing. And then this number here is actually the combination of Ki times N naught. So to do the problem, what we need to do is find both Ki and N naught. Now, Ki is, let's do it in blue, Ki clearly equals 0.3365 and actually has units of per day, and it needs that because it's multiplied by time here. And because we already know what Ki is, we can then say that the combination Ki times N naught equals 2.0173, and that number also has units of per day, right? So that thing, put it in parentheses because it's a number with units. And what we want to do is find N naught. So N naught, let's see if I've got enough room. We can write N naught equals 2.0173, 1 over days, divided by Ki, which we already know is 0.3365, 1 over days. And when you do the calculation, you get a number. What number do we get? I know we get a number. It's close to 6, right? So 6.00. And it doesn't have any units, right? Because these units here, let me do this, right? That cancels with that, and we end up with a number with no units. All right. So what we were doing is we were talking about we need to get to question 12.09. I just wanted to mention something about these yellow boxes. These yellow boxes, the about what you discovered, what these guys are about is it's about telling you something that'll make sense after you've done the fit. So in our fit, we found that the data fit to this trend line, and the trend line, as you can see, is a little above the points here at the end, and I think any person looking at this would go, oh, okay, well, it looks like the actual data are trending below. But it turns out you have to be really careful about that. And so read through that thing. I'm not going to spend a lot of time about it now. But now what I want to do is get back to question 12.09. What we want to do now is so what we're going to do is we're going to do a least squares fit. So this is kind of tricky if you haven't seen it before. It's actually in chapter 6 of the book, so I'm going to go through this and explain what this means. So actually we talk about residuals in chapter 4, so I'll talk about what those are, and then we'll talk about what equation 6.11 is. And the PowerPoint, if I can find it, there it goes. The PowerPoint, the next page of the PowerPoint, if I put it in full screen mode, is about calculating residuals. Alright, so from chapter 4, we know that a residual R, it's a good pirate letter, R. Residual is the difference between the observed and the expected values. So observed means like the experimental value, or in our case, the value reported by the European CDC. And expected is the number that the theory would predict. And so the idea of a residual is that it's the observed minus the expected. All right. I think that's a pretty straightforward thing. So in the spreadsheet, you can just calculate. We have a column for residuals, and we can fill that in. Then the next thing we want to do is we need to calculate the residual squared. And so the reason this has a subscript is because we're going to add up all the r squareds in the column. So square r to get r squared, and then this, why is that not working? Scribble, there we go. The square of the residuals, this symbol here means take the sum of all of them. Okay, so this is the sum of the squares of the residuals. And so it's the sum, it's what it says here, the sum of the squares of the residuals. Who knew? All right, so that's what we're going to do. So we're going to go back to our spreadsheet, and we're going to fill in the columns that have that stuff in them, and we're going to put the theoretical value. So here's the theoretical value. And remember, the formula that we're going to use is that the rate, the theoretical value for the rate, is given by equation 12.6. Okay, so equation 12.6 has, the formula is Ki, so it's equals Ki, and I need F4 for the dollar signs because we always want to use that one, times N0, and we always want to use that, so dollars for that guy too, times, and then in Excel, the exponential function is exp, open paren, and then we need to put in what that's going to be, and it's going to be Ki, and we need the dollars again, times time, and the time is the value of time in the same row. And then if we hit enter, we'll get the prediction of what that should be. So our unlimited growth model predicts that on day one there will be 2.8 people newly infected on day one. Ri is, remember, it was the observed, so the observed is 6, that's the number reported, it's the real number, and then you subtract the expected value, which is the theory prediction, so that's all the residuals are. And then R squared is just the value of this squared, and you can do hat 2. Alright, and we can fill in this whole table just by left click dragging, start in the middle and left click drag across. Go from here, the open cross changes to a closed cross, left double click, and it fills in the whole table. Alright, so if we go back to the instructions, it's always good to go back to the instructions. It says, in part A, it says, before you do anything else, delete the Excel trend line and add a series to your graph to show the prediction of equation 12.6. Okay, and record your graph. Okay, so let's do that. So go here, we want to delete the trend line, so just highlight it, hit delete, and then we want to add some new data. And the way to add new data is you click on the graph, then right click on the graph, find select data, and we need to add, and we need a good name for this. So this is the unlimited growth theory or model, and it's equation 12.6. I like putting the equation numbers in because then you know what equation we were thinking of. The x values, so let me just remind you how that works, right? When we're selecting them, click on the selector tool, this up arrow, click on that, and then you can highlight the numbers you want for that, for x, and the values you want for y are here. Click the selector tool, and you can highlight all those y values, and you should get a series plotted, and you'll see there it's in orange, and I'm going to click OK. Now, because this is a theory curve, we don't actually want it to be points, we want it to be a line. So I'm going to right click on there, go Format Data Series, and then click on the paint thing, and I do want a line, so now it added a line, and I want to get rid of the markers, so click on marker, and it's kind of weird, you have to click on marker, and then marker options to find the place where you can say no markers, thank you, say none. Alright, so there you go, we can do that. I'll just leave it like that. So you'll see here's our legend, and it shows that that's what our current values guesses for Ki and N0 give. Alright, so that's what you had to do for this part. Let me go back to the question. Alright, so, and then it says, and this is the bit that you probably need some help with if you haven't taken my class, using the techniques we learned in chapter 6, use Excel's solver to do a least squares fit to equation 12.6 and record your least squares fit to the USA data up to day 19 of the COVID-19 epidemic, and then record your graph. Alright, so let's talk about that. We should save this as B, so let me go back to the spreadsheet. There it goes, and I will save it. So file, save as, actually let me just make sure I save this one, seeing it was the final one we had. So I've saved it for part A, and now I'm going to do file, save as for part B so I don't overwrite A. B. So save that. And now what we need to do, we actually have everything in place. These are the parameters that are just numbers. Q is that thing that I said. It's the sum. See the formula up here? It says sum of those things. And if I click in the formula bar, it actually shows me the things that are being added up. So that rather mysterious looking symbol, where do I find it? Oh, it's over here. Right, this guy, I don't need to make it big. Right, this guy right here, this Greek sigma is actually telling us the sum of all the r squareds. So that's actually what Excel is doing. It's actually summing up all the r squareds. So don't get messed up by the hieroglyphics of math. That's all it means. Alright. So now we need to use Solver. So if you don't have Solver installed, you'll need to go to Help and have it installed. But if you do have it installed, the way you find it is you click on the Data tab, and then Solver will be right over here at the very right hand end. And if it's not there, go to Help, right, the Excel Help, and go just type in Solver, and it should tell you how to install it. Alright, so I'm going to click on Solver, and it gives you this dialog window for all the parameters for Solver. And the objective that we're going to have, I'm going to click on the selector tool and click on the thing. What we want to do is minimize the sum of the squares of the residuals, which is what Q is. So that's what we're going to do here. Then I click on the selector tool again, and so you'll see it put $7, which is this cell over here. The thing that we want to do, we don't want to maximize it, we want to minimize it. We want to find the smallest value of Q, and we're going to do that by changing variable cells. So the variable cells I want to change, click on the selector tool, and then click on KI, and then hold down Control, and if you've got a Mac, you have to hit down Command, click on that one as well, so it highlights both of them, and you'll see this is $A, $3, comma, $A, $5. Then click on the selector tool again, and we're now ready to get Excel to do its magic with Solver. What Solver does is it will adjust the two parameters that we had that asked it to change until it finds the smallest value for the Q. So let me go here. Okay, so if I hit solve, it takes a little while. It's going to do some calculations. What it's doing is adjusting the whole spreadsheet, and then you get this thing. Now you should always read these things carefully. The first thing it says, Solver has converged to the current solution. All constraints are satisfied. Solver has performed 5 iterations, so that's like steps, and it didn't move significantly. And it then says, if you want to get it better, use a smaller step. What we're going to do is just say OK. And what I usually do with this is I actually run Solver again. So I'm going to click on Data, and I didn't need to Solver, and then do Solve. And this usually goes pretty quick when you've already done it once. And it might change things a little bit. And it says OK. And so there you go. So let's have a look at this. Can you see now that the orange curve is now matching the blue dots a lot better? It's actually going through them quite well. It's changed KI. Remember, it was 0.34, and it's changed N0. Remember, N0 was 6 before, and now it's 23. The other thing you should notice is that this orange curve, can you see how it's kind of bisecting these points fairly evenly? That's what the least squares fit does. It's really the most widely used way of fitting data in science. Alright, so that was, where are we? I have to go back and just make sure I'm reading the right question. Yes. Oh, no, this isn't 8. We are doing, this is 9, so I should have saved this as file, save as. This is annoying when you forget to do this, right? Save it as question 9b. Yes. Alright, so that's our answer for 9b. And it's now the least squares best fit, right? The orange curve is now going through the data. And when you look at this, I think you'll agree that the model seems to do a pretty good job of explaining what's happening in the first 19 days of the epidemic. Alright, so we're nearly done. Now we're up to question 10. And in question 10, it says change the vertical axis of the graph to logarithmic scale. Oh, yes, so I forgot. So this is talking about question 8 and question 9. So I'm just going to do the one that we've currently got open. And so we're going to do B. So this is going to be question 10B. So let's do that. Save this again. File, save as, and call it 12.10B. There we go. And the question said change the vertical axis to a logarithmic scale. So let's just do that. So remember, you left double click on here, you get this, and if you get lucky the right thing pops up, the one with the bars, and you can click logarithmic scale, and then we need to move our legend out of the way because it's kind of an annoying place. Let's put it there. Alright. So what we now have is, you'll see that from about here on it's fitting the data quite well. It's not doing a terrifically great job with these ones, but you'll notice that these numbers are all, less than 20 or so. These are the ones where we started getting bigger numbers, right? Let's see, where's the place where they match the best? 8. So 8, that's that point where it's at 34. So you'll see that this is actually doing a much better job of the more reproducible larger numbers that happen from day 8 through day 19. And in the handout, there's actually a discussion of that and how it compares with Excel's trend line. So the one we just did is actually this gray line, and the Excel trend line is the dotted line. It might look better on here, but as the handout, the chapter talks about, this is actually a much better fit to the data. Alright, so that's all I've got for today. We're going to be doing more. I put in a link to a piece of pop music that I came across that I thought was interesting. If you're getting kind of had enough of this stuff about COVID-19, pick a pop song about stuff running around your head. It might be better. Anyway, so getting back to our PowerPoint, that's our last slide, and I just wanted to remind you, so all the materials that we have, the URL is circle4.com/biophysics, and you should look up the top for the links to the free chapters and other things. And I will be posting this video there just as soon as I get it uploaded to YouTube. Alright, and watch this space. We'll be coming back and doing the next section, which talks about how you can flatten the curve by reducing the infection rate.